Okay, guys, we're going to start a series. This is section 9.1. Its primary focus is geometric series, but we first have to define what a series is, and especially what an infinite series is. Um, an infinite series is a sum of an infinite number of terms, or basically taking a sequence and adding all the terms together. Obviously, this notation means summation. It's an easy way for us to write we're adding an infinite number of things. Um, an infinite series, there's a lot of ambiguity here. First of all, we're going to be able to determine divergence pretty well. But the fact that we can figure out if something's convergent is going to be a significant challenge. Um, and that's where we're working at, is to check for convergences. And here's the thing we do know. If we do know for in fact it's convergent, then we know for sure that as the limit as k approaches infinity, which is the number of the term. So the infinite term of the sequence will equal 0, or will approach 0. Um, we're really hoping, and we love geometric series. Geometric is a geometric sequence that we've now added together. Um, and basically, if it's geometric, it means it has a constant multiplier. If it has a constant multiplier, and think about multiplying, if you constantly multiply by a number smaller than 1, or more specifically between 0 and 1, you're multiplying by, like, say, half. Therefore, each time you multiply, it continues to get smaller and smaller. This is a significant part, because if you continue to do that, we're actually going to be able to determine that something converges. Not only that, we're going to be able to determine exactly what it converges to. In other words, we're going to be able to add up an infinite number of numbers if it's a geometric sequence. So in a sense, to know it's a geometric series, first of all, if you establish it's a geometric series, we can tell it converges if the R value is between -1 and 1. This is considered our interval of convergence. In other words, it's the values of R that allow it to converge. Any values outside of that will not converge, in a sense, will diverge. Uh, for example, if I use R as 1 and I continue to multiply by 1, it's absolutely doing nothing to the term. So each time you're adding the same exact number over and over again, it won't converge. And of course, if you multiply by a number bigger than 1, you have a situation where obviously the number keeps getting bigger. So if you add them all the terms together, you're not going to get you're not going to know what it goes to. It's going to diverge. Note, should be familiar to you, this format here. Note that A is your first term, and R is your constant ratio, or in other words, it's your constant multiplier. So what we're looking for is, basically, we're looking for a constant multiplier in our sequence. If we have that, we have geometric. If we have geometric and the R values between -1 and 1, we score. We have all this great, wonderful stuff. Let's look at a couple examples. Yeah, if you look at this set of numbers, this sequence of numbers, and we add them all together, it seems pretty obvious that as the numbers keep getting bigger, if they keep getting bigger and I add them all together, I'm probably not going to get convergence. It's probably diverging to infinity. So here's some ways we can write that and determine and assess that. If I use the capital letter S and put a little subscript 1, that means the sum of the first term only. In this case, it's just 2. If I want the sum of the first two terms, I would say that's 4.2. Why? Because I add the first two terms together. S3 would follow that. I would add first, second, and third term together. Now I'm about ready to have fun. That's 6.42. And if these sums are continuously getting larger and the difference between them is not, then it's divergent. So this series is divergent, or it diverges. The next example here, this one, um, first of all, anytime I see a series, I'm going to write them out. I'm going to write each term out. And as I do so, I'm hoping that each term will demonstrate a constant multiplier. Here, I can assess that the first term is 1. My ratio is, well, let's see. If I multiply by 1/3, I get 1/3. If I multiply by 1/3, I get 1/9. If I multiply by 1/3, I get 1/27. So that is good. And that's really, really good because I have a geometric series, which this is, we've clearly shown it is. This guy is in the interval of convergence. So I know for sure this converges. Not only that, because it converges and it's geometric, see this right here? That's the geometric series. It will, as long as it converges, equal that value. So if I wanted to add up all these numbers, etc., 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 I know that in fact it will equal a over 1 minus r, which will give me 3/2. I have now added an infinite number of numbers together. And it's very true, I can always do that with a geometric series, which this is. Let's go on to the next one. Example. If I take, well, first of all, I look at the sequence and I say, well, is it geometric? If it's geometric, I'm in love with it. A couple of other ways to do that is if I want to call it a multiplier, sometimes I can just simply take the ratio of the two numbers. Usually put the top one on top. I don't know why I put the bottom one on top. So you do this and you say, oh, that's 0.1. Or in other words, I'm multiplying by 0.1 each time. Let's see if that's true. If I multiply again, I get 0.1. And I also get that multiplier. So I can see now that it's geometric. So my first term, A, is 0.2. My R is 1/10. I have clearly established that it is going to converge. And if it converges, this whole sequence or series of numbers equals A, and I'm actually going to write that as a fraction, 2/10 over 1 minus 1/10. A over 1 minus R, which will equal 2/9. Just to kind of point this out to you, notice something. 2/9, if you divide that, gives you 0.22222. 3/9 would be 0.33333. 4/9 would be 0.44444. And if you look at that, that's in fact what you're going to get if you sum all these up. It is a non-repeat. It's a repeating, non-terminating decimal. Therefore, it's what we get when we divide by 9. Okay. Now here's another situation here. The question is, does it converge or diverge? If it does converge, state its sum. That means tell me what it adds up to. This is written in the summation form. So I'm going to do is I'm going to go ahead and write out the terms. So the first thing is you plug in 0. So you get 5 to the 0 over 6, 0 plus 1. Plus, the next term would be 5 to the 1 over 6, 1 plus 1, etc. So let's write those out. So my first term is 1. My first term is 1 over 6. Plus, my second term is 1 over 6 times 5/6. Plus, My next term would be 1/6 5 over 6 squared. That means that I know what my first term is. I also know it has a constant multiplier. I can see that in my terms. My constant multiplier is 6. So I can conclude that this summation converges, and it converges to a over 1 minus r, which equals 1. Hope I didn't make any mistakes. All right, moving on. A couple more examples here. Notice that this time, again, I have a summation. Notice this time that it's variable. It has an x in it. It's a variable. That means we can make it whatever we want to. If I wrote this out in process, my first term is 3, and then it's this thing to the 0 power, which is 1, plus my next term would be 3x minus 1 squared over 2, plus 3x minus 1 over 2 squared. So I can see it's geometric. It has a first term, and it has this constant multiplier. Okay, so I know it's geometric. My A is 3. My R is variabled. That means I can change it. Is x minus 1 over 2, and I can choose the x I want. But here what we're interested in doing is making it more specific. I want to know what x values make this converge. We know this is true. It will converge if that's true, because that's the interval of convergence. My R is x minus 1 over 2. Which now I need x. I need to know what the values of x are. So I'm going to go ahead and multiply both sides by 2 and add 1. These are the values of x right here that if I use any number in that area from -1 to 3 and I plug it into my series up here, if I plug it in here, I plug it in for x, any number between -1 and 3, I know that those values will create a convergence. Now, again, the same token, I'm going to take this summation or this series, and I'm going to tell you what function is produced. In other words, I can create a explicit formula where I can find exactly what it equals as long as you tell me the x. Very similar to before, I'm going to take a over 1 minus r. Usually create some fractional work. Be cautionary about this. So I'm going to simplify that. There's my function. This is the actual function. You tell me what x it is, I can tell you what the sum will equal. So I'm going to go ahead and get a common denominator at the bottom. I'm going to flip it over. And I'm going to simplify that bottom. And there is a function for my series. This is a function. This is written as a summation. So the series is actually equal to both of these. One is a function. There's your fun. And here's your series. Or summation. What the heck? A power series? Are you kidding me? What the hell's that? Well, power series is the series. And we can look at it, and we're going to view this in two different ways. I need some space here, so I'm going to get rid of this right now. Hopefully you got that written down. If not, pause and go back. Nice thing about videos. All right, we know these two things. We're going to look at the function for the series that we just did, which the function was, and wow, I just erased it. Okay, is this one. It is equal to this series. Okay, what we're going to do is we're going to write out we're going to take the derivative of first the function, and then we're going to take the derivative of the series um, and get a series for the power function. First of all, if we just want the derivative of the function, then all I have to do is do a quotient rule here. So derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So if I want to write this as the power series as a function of its derivative, then I've got 6 over 3 minus x squared. That's the easy one. The other one takes a little bit more work. And a little intuitive work at that. So what I'm going to do is first I'm going to write down um, I'm going to jot down here what I'm seeing. I'm seeing 3u to the n. Uh, so if I want to take the derivative of the series, a couple notes here, I'm going to go ahead and go uh, multiply by the power times u to the take once off the power and then times your u tick. So that's basically what I'm doing here. So I'm going to go, so my new series is 3n u to the n minus 1 times the derivative of the inside of my u, right here, my u, which is 1/2. So my new series, the series for the derivative is 3/2 n x minus 1 over 2 n minus 1. Now, because the dynamic shift of a derivative, you're losing a power, that makes us start, that it used to be a 1, we're now going to start at, it used to be a 0, now I'm going to start with 1 and go to infinity. Okay, now we're going to do the same thing with the integration. So we're going to do it two ways. We're going to look at it in terms like we did before. We created a series for it, or summation for it, and we created a function for it. Now I'm going to do the same thing. I'm going to take that original 2. My function was, I lost it again, 6 over 3 minus x. And it's equal to its series, which was n equals 0, 3x minus 1 over 2 to the n. Okay, so those are the two things we're going to do. Now we're going to do the same thing, but now we're going to create a power series for the integration of those. So if I want the integration of f of x dx, this is the one that's probably more simpler of the two. I'm going ahead and integrate that and pull the 6 out. And I believe, if I'm not mistaken, I've got a u there, which is 3 minus x. My du would be negative dx, so I got to be careful with that negative. Concluding that 6ln 3 minus x, and then I need a negative. I now have, right here, I have the power series for the integration of that function. Now, if it's written as a series, summation, we're going to look at it very similar again. I'm just going to integrate that nth term. So you got 3x minus 1 to the okay, dx. Always got to have those dx's. Some of you left them off on your test again. That would lose you points in FRQ. Anyway, obviously I'm going to pull out the 3. Okay, now remember, I'm going to treat n like a constant here. So, and I'm going to have a u here. So let's do u substitution. U equals x minus 1 over 2. Du equals 1/2 of the dx. So my dx equals 2 du. Okay, here we go. Integration of u to the n dx is now du, but I got to put a 2 on the outside, which makes this 6. Okay, now we can integrate. Antichrist, bada bing, bada bing, bada bing, bang, bang. Oops, I know. It should be +1. Don't yell at me. +1, which leaves me the following. 6 over n plus 1. I'm putting the n plus 1 with the 6 because the n is a constant. And then I have u. Again, u was, I'm not getting anything out of u, so I'm going to go back to my x's. Was that n plus 1. Now I can just tack on the summation series, the bounds, and we're done. Okay, please note I'm posted up the bookwork. You want to get that started. I know there'll be questions. It's cool, like always. Get them started, bring in your questions, and I will see you tomorrow. Thanks.